A snail is crawling in an underground tunnel, which consists of n circles. For example, in the illustration, we have that n is equal to 3. We assume that every 2 circles intersect at 2 points, and no 3 circles pass through the same point. Initially, our snail slides on one of the circles in a clockwise direction. Then, when it reaches an intersection point, it moves to the other circle. But now, it slides in the opposite direction. For example, we see in the illustration that our snail reached an intersection point. Since in the previous circle, it slided clockwise, now, it will slide anti-clockwise on the new circle. Now, our snail reached another intersection point. Since it slided anti-clockwise on the current circle, it will jump to the new circle, while sliding clockwise. That is, our snail alternates his direction from clockwise to anti-clockwise and vice versa, each time it reaches an intersection point. We have the following main problem. Prove that if the number of circles n is even, then our snail cannot cover all the circles. For example, let us note how our snail slides, in case that we have 2 circles. As we can see, our snail returned to the starting point without covering all the circles. Since it will make the exact same movement in the next round, it will never be able to cover the circles. Let us now check the case of 4 circles. As we can see, we are again in a situation where our snail returned to the starting point without covering all the circles. Hence, we showed that for some arrangement of the circles, where n is equal to 2 or 4, our snail cannot cover all the circles. To prove our main assertion, we will actually prove a more generalized result. We relax the condition that any 2 circles must intersect, and instead assume only that the union of our circles forms a connected set. In the illustration, we can see an example for such family of circles. We will show that, for such more generalized families of circles, our main assertion also holds. For this, we introduce the concept of odd regions and odd intersection points. Observe that our family of circles divides the plane into regions, including the infinite unbounded region. We say that a region is odd if it is contained inside an odd number of circles. For example, the following regions are odd. Similarly, an intersection point of two circles is odd if it is contained inside an odd number of circles. For example, the following intersection points are odd. Let R odd and P odd denote, respectively, the sets of odd regions and odd points. Then, if n denotes the number of circles, then we have the following two lemmas. Lemma 1. The number of odd regions minus the number of odd points is equal to n modulo 2. Lemma 2. If our snail covers all the circles, then the number of odd regions minus the number of odd points is equal to 1. Observe that these two lemmas together implies that n is equal to 1 modulo 2. That is, n must be odd, which proves our main result. Hence, to prove our main assertion, all we need is to prove lemmas 1 and 2. Let us start with lemma 1, and show that the number of odd regions minus the number of odd points is equal to n modulo 2. Let C denote the set of all circles. For a circle inside C, let RC and PC denote, respectively, the number of regions and points inside it. First, we claim that we have the following two equalities. Let us check that the first equality is true. The second equality can be verified similarly. We need to check that the number of odd regions is equal to the total sum of regions in each circle, modulo 2. Let us look at the illustration for a reference, and let us take a region which is found inside an even number of circles. Observe that this region is summed an even number of times in our equation. This is because each time we take a circle, we count all the regions inside it. And since our region is inside an even number of circles, it will be summed up an even amount of times. Hence, after taking modulo 2, its contribution to the sum in our equation will be 0. Hence, the even regions do not contribute to the sum in our equation. In the exact same way, we can show that each odd region is counted an odd number of times in our equation. Hence, after taking modulo 2, each odd region will be counted exactly once in our equation. Since each odd region is counted exactly once, the sum in our equation will be equal to the number of odd regions, which is exactly the left-hand side of our equation. Hence, we showed that the equality is true. For a circle C, let XC and AC denote, respectively, the number of circles which intersect C and the number of arcs inside C. Our next aim is to show that the number of regions inside C minus the number of intersection points inside C is equal to the number of circles which intersect C plus 1. For this, we use Euler's theorem for a planar graph G, which claims that its number of faces minus its number of edges plus its number of vertices is equal to 2. Now, let us take a circle C. Since the number of circles which intersect C is equal to xc, it follows that there are 2 xc intersection points on C, and these intersection points divide C into 2 xc arcs. Hence, by Euler's theorem, we have that the number of regions inside C, together with the infinite unbounded region, minus the number of arcs on and inside C, plus the number of intersection points on and inside C, is equal to 2. Hence, we obtain the following first equality. Now, let us look at the circle C again. We have 4 arcs, starting from every interior point inside C, and a single arc, starting from an intersection point on C into an interior intersection point. Hence, if we count the number of interior arcs, which start from each intersection point on and inside the circle C, then we obtain that the total number of arcs is equal to 4 times the number of the interior intersection points, plus the number of intersection points on C. However, in this process we actually counted each arc twice, and hence the right equation is as follows. Hence, from this equation, and the equation we obtained earlier, we obtain the equation at the bottom line, as needed. Now, we can finish the proof of Lemma 1. Indeed, by summing the equation we obtained on the set of all circles, we have the following equation. However, as we proved earlier, the first and second terms can be replaced by the number of odd regions and the number of odd intersection points, respectively. Observe that the sum on the number of circles which intersect each circle in the sum must be even. This is because, if 2 circles C1 and C2 intersect, then C1 is counted in xc2, if and only if C2 is counted in xc1. Hence, we obtain that this sum is equal to 0, modulo 2. Thus we finally have that the number of odd regions minus the number of odd intersection points is equal to n, modulo 2. Now, all is left is to prove Lemma 2. That is, we need to prove that if our snail covers all the circles, then the number of all odd regions minus the number of all odd intersection points is equal to 1. For this, let us introduce the concept of the generated curve from the snail's path. Let us start from the example of 2 circles, and let us assume that our snail starts its path on the upper part of the upper circle. Then, as our snail starts sliding until it reaches its starting point, we see that the curve on which our snail moved on is as in the illustration. On the other hand, if our snail starts its path on the lower part of the upper circle, then, as our snail starts moving until it reaches its starting point, the other curve that is generated is as follows. Hence, in summary, the curve that is generated from the snail's path is the following disconnected curve. For another example, let us consider the following three intersecting circles. As our snail starts sliding, keep moving, and then, finally, reaches its starting point. The curve that is generated from the snail's path is as in the illustration, and the curve that is generated will be the same, no matter in which point our snail starts moving. This is because our snail covers all the circles, no matter what is the starting point. Hence, as we can see, in this case, the curve that is generated is simple and connected. Our main observation is that our snail covers all the circles, if and only if the corresponding generated curve is simple and connected. Now, let us start with a set of circles, which, by assumption, can be covered by our snail at one phase, by starting at any initial point. Hence, the curve that is generated from this set of circles is simple and connected. We show now how to use this curve in order to prove that the number of all odd regions minus the number of all odd intersection points is equal to 1. First, we show that all the odd regions are inside our curve, while all the even regions are outside. For this, let R be an odd region, and let X be a point in R. As is well known, a point X is inside a simple, connected curve gamma, if and only if each ray which starts at X and is not tangent to each point of gamma, then it intersects gamma at an odd number of points. Now, let Y be a ray emanating from the point X. Observe that each circle C, which contains X, intersects Y at only one point. And hence, any such circle contributes 1 point to the intersection of our curve with the ray Y. For any other circle C, which does not contain X, since our ray is not tangent to C, it will intersect C at 2 points, or not at all. Hence, any such circle contributes an even amount of points to the intersection of our curve with the ray Y. Hence, since there are an odd number of circles which contain X, then the ray Y will intersect our curve at an odd number of points, as needed. At the same way, we can prove that if X is inside an even number of circles, then our ray will intersect our curve at an even number of points. Let P be a point of intersection of the circles C1 and C2 in our set of circles. Let us consider a small neighborhood around the point P. Let R1 and R2 be, respectively, the regions which are outside and inside both the circles C1 and C2. Let R3 and R4 be the two remaining regions, such that each one of them is exactly inside one circle, C1 or C2. Now, assume that the point P is inside exactly K circles. Then, R1 is also inside these K circles, and R2 is inside these circles, and also inside C1 and C2. Hence, R2 is contained inside K plus 2 circles. As for the regions R3 and R4, each one of them is contained inside exactly K plus 1 circles. Let us replace now the neighborhood of the circles C1 and C2 with the corresponding generated curve. Then, the regions R1 and R2 get connected, while the regions R3 and R4 remain separated. Hence, if P is an odd intersection point, that is, K is an odd number, then R1 and R2 are also odd regions, and hence the new connected region is created from two odd regions. Similarly, if P is an even intersection point, then R1 and R2 were even regions that got connected. Let us return now to our generated curve, and let us emphasize the set of odd regions and odd intersection points in our original set of circles. As we have just proved, the odd intersection points are exactly those neighborhoods for which the odd regions are getting merged together. Hence, if we replace each odd region with a vertex, and each odd intersection point with an edge that connects the two corresponding merged regions, then we obtain a connected graph. Observe that this graph must be a tree, that is, it has no cycles, since our generated curve is closed, simple, and connected. Hence, its number of vertices must be greater by 1 than its number of edges. This is exactly equivalent to the fact that the number of odd regions minus the number of odd intersection points is equal to 1. Hence, Lemma 2 is proved, and thus we finally proved our main assertion,